So now let's look at some code for the dogs versus cats, for the dogs versus cats transfer learning problem. And we will use VGG16 trained on ImageNet, right? There is actually a brilliant blog on the Keras blog itself. I'll provide a reference link to this URL. And this blog is written by Francois Chollet, who is actually one of the co-creators or one of the core contributors to whole of Keras. He started the whole Keras project. If I'm not wrong, he currently works at Google Research, working on integrating Keras deeply into TensorFlow and other machine learning and deep learning problems, right? We look at some simple example here. So let's assume I have, let's take a data set, right? Let's assume I have 2000 training examples, right? So my data set D is basically 2000 xi comma yi, right? I equals to 1 to 2000. So I have only 2000 images. I have 1000 images for each class. I have two classes. So my yi can be cat or dog, right? Two class classification problem, and I have 1000 images. 2000 images is quite small to train a state-of-the-art convolutional neural network, right? So, and all of my data is organized like this, right? I have a folder called data, in which I have a subfolder called train. I have the images of, I have a folder called dogs, in which all dog images are there. I have a folder called cats, in which all cat images are there. This is my training data folder. Similarly, I have a validation data or a test data or a cross-validation data, in which again I have a folder called dogs with all dog images and all cat images, right? And this data has been taken from Kaggle, right? Even though Kaggle has 12,500 cat images and 12,500 dog images, we will just use 1000 cat images and 1000 dog images. All these have been gotten from Flickr. Flickr is used to be owned by Yahoo. I think it was recently sold to some other company. So Flickr is basically an online repository where you could store images like Google's Picasa or Google Photos, right? And what they've done here is they've taken 1000 images for each class in the training and 400 additional samples for each class in the validation. So your dtrain contains of, your size of dtrain is 2000, your size of dtest is 800, 400 images of each class type, right? And if you want to look at some images, these are how your cats look like. You have cats in various lightings and various types of cats, similarly various types, various breeds of dogs with various backgrounds and things like that, right? So let's look at the simple thing. First, let's do some data pre-processing and augmentation. This is a very simple code snippet to perform augmentation. Very, very simple code snippet to perform augmentation in Keras, right? You just say Keras pre-processing image import data generator, and you just say I want to rotate it by 40 degrees. I want to create new images by shifting, by width shift, horizontal shift, by vertical shift, by rescaling the images, by shear, zoom transfer, flip, all sorts of things, right? And I want to create a data, so I'm creating a data generator, right? Which is basically a data augmentation step. And once I create this, the way I'll operate is this, right? This is my data generator, right? And there is beautiful documentation of Keras. If you want to read more about image data generator, you can simply Google search image data generator Keras. You'll get terrific documentation. I really like Keras for its documentation. It's very, very well documented. It explains everything that you want with some nice example. This feels very much like scikit-learn to me. The amount of documentation they have is phenomenally good, right? So then what I do now is for each image in my data set, right? I will basically apply this image data generator or image augmentation or data augmentation strategy so that I create more images. So just to give you an example, if this is my input image, right? These are all the other images after data augmentation. If you notice this has been shrunk. This has been flipped. So there are a lot of these similar images, whether the black cat is on the right side or left side, it should not matter, right? So they've done all of this data augmentation, and there's a very nice code snippet here to explain you how this is done. And this blog is very, very readable. Anybody can read it. So as a baseline model, what they will try to do, the first step here is let's build a ConvNet model from scratch. Very simple with 40 lines of code, right? So let's see a code snippet for the baseline model. You can actually get the whole code here. If you click on this, for example, if you click on this, right? If you click on this link here, it will open up a very nice snippet here, which will tell you how this simple model is trained. This is a very, very simple model, right? Your first model is a very simple model where you're training a simple neural network from scratch. Okay, you're training a small convolution neural network from scratch. And how does a convolution neural network look like? It's a sequential one. You have a convolution layer, your activation is ReLU, you're adding max pooling. So this is one layer of convolution followed by max pooling, another layer of convolution followed by max pooling, again convolution and max pooling. And then once you come here, I flatten the data, right? I flatten the data, a couple of dense connections with a dropout, again dense connection, and my activation is sigmoid finally, because I have a two-class classification, right? And my loss is of course binary cross entropy, which is nothing but two-class log loss. And my optimizer is RMS prop. I also want to get the accuracy, right? And of course, I'll train this model and run it. Very, very simple. The whole code looks like this. I have a batch size of 16. This is my image generator, my training data generator, my test data generator. And at the end of it, I'll just run the code. And at the end of running the code, right, I'm running it for a bunch of 2000, I'm running it for 50 epochs, things like that, right? So I get an accuracy of about 79 to 81% after 50 epochs, right? So roughly around, let's say approximately 80% accuracy is what I get if I train my own neural network from scratch. And remember, I have very little data, so I can't train a very, very complex VGG16 like network. I'll simply overfit them, right? So if you use a simple small convolution neural network from scratch, you're getting 80% accuracy, literally 40 lines of code. That's how simple Keras is, by the way. So this is your classical convolution neural network training. Let's go one step further. Okay, what if I use the bottleneck features in a pre-trained network? Okay, so let's use so the images that I showed you in the previous video are from this blog actually, right? So what are your bottleneck features? Bottleneck features are all the features except the top layers. Okay, I'll just remove the top layer. I will use this as my convolution features, right? And I'll train another model on top of it, right? And how do we achieve it? There is a very nice code snippet here. Again, if you click on this, let me just click on this. Okay, it's going to GitHub. It will give me a very nice code snippet again here. Okay, and the most important thing, the most important line in this code snippet is this. I'm saying my model is from applications folder, get me my VGG16 model. And here I'm saying include top equals to false. And I want the weights that have been generated by training on ImageNet. When you say include top equals to false, what it would eventually do for you is it will give you the whole VGG network except the top layer. Right? Everything else it would give. Now I will use this. Now I will use this model, right, to generate my CNN features, right? And my final model will be like this, right? I'm actually generating. So there are two functions here. Save bottleneck features, where each image is taken and I generate the bottleneck features and I save it to a NPY file. And then there is another function here where I read all of the bottleneck features for each of the data points. And then I build a simple MLP on top of it. This is an MLP, right? Where I have a flattened layer followed by a dense layer, dropout, dense. That's it. This is an MLP. So what have I done? I've used the VGG16, right? I removed the top layers. For each input image, I generated xi hat. And on top of it, I built a very simple MLP, two-layer MLP, right? Because I have a dense layer and I have a dense layer here. Just literally one hidden layer. I have only one hidden layer with ReLU activation, and then I have a sigmoid, which is my output layer. Right? This is basically one hidden layer MLP. Very, very simple model here. And all the code is readily available for you here. Right? And when you train this model, and when they train this model on this data set, right? Here is an explanation of the code. When they trained it, they got an accuracy of 90 to 91%. Right? Look at this. Look at this. This is the fun part here. Right? So let me go back and write it down for you. So when you trained a small convolution neural network, a small convnet on your own, you got roughly about 80% accuracy. So when you did VGG16, when you used bottleneck features, right, we are getting about 90%. And this can be done very, very fast, right? Because I'm not training anything. I'm just reusing what already exists. This takes some time because I'm still training, even though it's a small convnet, I'm still training a convnet. So this is a much faster, right? Because I'm not training any convolution neural network. I'm training a simple MLP, that's it. And still I'm getting a much better accuracy, right? So this is case 1, this is case 2. Case 3, this is also interesting. Okay, what if I want to fine tune the top layers of my pre-trained network, right? Like these, I want to fine tune them. There's a very nice code snippet again here. If you just click here, you'll get a nice code snippet. Okay, again, here this code is also very, very interesting. So here, when you load the model itself, you're saying load the model VGG16 and don't include top. Just don't include top here. Okay, keep everything else. And when I'm defining my top model, see, this model VGG16 is this. So I've taken the top part of VGG16. So what am I left with? So let's assume this is my VGG16 model. I'm saying include top equals to false here, which means this part won't be there. So I'm only left with this. And in this case, I want to keep all of these weights as constant. So I will only take the output from here and build a model, build maybe a couple of layers here. And I want to keep these constant. So what am I doing here? When I'm defining my model, I'm saying just flatten the output that you get from model. Okay, so my input image goes here and I just get the output which I get here. Whatever is the output that I get here, I'm defining my top model. I'm defining my top model on top of it. And I'm not doing any optimization on these, which means all these are kept constant. So I'm using this just as a function, right? I'm saying just model.output shape. Take the output, use this as a black box. Whatever input you get, take the output and build a model on top of it, and you fine tune this. And this model itself, you can have, of course, you can have convolution layers here, or you can have just the topmost layer if you want. In this example, they just have a ReLU unit and a sigmoid unit, right? So this is another example of how you can just modify the later layers without touching the previous layers, right? So, and when you do that, okay, sorry. So when you do that, right? So when you do that, again, you get pretty good accuracy. You almost get like 94% accuracy here, right? So this is VGG16 plus train your top layer or your last layer, right? You're getting almost 94% accuracy here. And this is also quite fast. This is also very, very fast because you've kept most of the model constant, right? All the early layers are kept constant. All the early layers are kept constant here, right? Even this is quite fast. Of course, this might be slightly slower than this, but it's very fast. It's not very, very fast, right? So these are very simple strategies. And what we can do, obviously, there are more steps that we can achieve, and you can go above 0.95 accuracy in 50 epochs by doing some of this. You can do more aggressive data augmentation. You can add more aggressive dropout to avoid overfitting. You can add more regularization like L1 and L2 regularization. You can add more convolutional blocks. For example, in this code example that you'll see here, what they have done here is they didn't fine tune any of the convolution layers. They only fine tuned this layer, right? You can choose to fine tune the last 3 layers instead of just, or last 3 blocks of layers instead of just the last layer or last block of layer. That's an option you have. Of course, you need more data for it, right? And for this case study, for every segment of code, you can get the full Python code. For example, here, if you just click, you get the Python code. And if you want to try it on your own, right, it's very, very simple. You just download this whole code, paste it in your IPython notebook and run it. That's it, right? You can just copy this whole .py file, or you can just copy this whole text, the whole code here, paste it in your IPython notebook and you're good. So I really like this blog and I want to spend some time on this blog with you because this blog gives you very, very nice details on how to do actual transfer learning in Keras with all the 3 cases. Look at this. It has given you all the 3 cases, right? Where you're training a convnet from scratch, where you're using the bottleneck features, and where you're fine-tuning just the top layer. Of course, there are more complexities. This is just a tutorial, but this tutorial is nonetheless very, very good tutorial. This is one of the best tutorials I've seen for transfer learning in Keras.